Welcome to this third and final lecture on the physics of magnetic resonance imaging. After this lecture, you should be able to outline the basic components of an MRI system and their function, and also understand some of the safety issues related to magnetic resonance imaging. Here is an overview of a typical superconducting MRI system. We start with the superconducting magnet here, which we are seeing in cross-section. The magnet contains windings of a special alloy of niobium and titanium, which when it is kept at the temperature of liquid helium, 4.2 Kelvin or minus 269 degrees Celsius, it becomes superconducting, which essentially means it has zero electrical resistance. When the service engineer first installs your magnet, he will inject several hundred amps into those windings, and that current will continue to circulate unimpeded because of the zero resistance until the magnet needs to be de-energized for some reason. Because liquid helium is quite expensive, there is normally a cold head or cryocooler mounted on the magnet. This is a very high performance refrigerator that works to keep internal radiation shields inside the magnet assembly very cold to try and minimize the helium boil-off. The cold head is connected via helium lines through a waveguide in the RF cabin into a compressor in a separate equipment room. Should the magnet ever cease to be superconducting, then the large amount of energy that is stored in the windings will be converted to heat. The liquid helium will be vaporized and will increase the pressure within the magnet. Again, there is a burst disc at the top here, which will rupture when the pressure exceeds a certain value, and then the helium vapor will be vented through the quench pipe to the outside of the building. This is important because helium can potentially asphyxiate people since it displaces oxygen, and it is also extremely cold. Inside the room temperature bore of the magnet, we have the gradient coils connected to high power amplifiers for the X, Y and Z gradients, and they have appropriately filtered electrical connections through this RF cabin, which we'll talk about in a moment. Inside the gradient coil, we have the whole body transmit coil, typically of a birdcage design, and although it can also be used for signal reception, it is mainly used to create a relatively homogeneous transmit field inside the magnet. The transmit coil is connected to the RF transmitter and amplifier, again through filtered connections in the radio frequency cabin. Then we have the receiver coils, which are generally arrays of small elements that are positioned as close as possible around the anatomy of interest of the patient, and each of these individual coil elements are then connected to a radio frequency receiver and spectrometer system, where the analog signals from the coils get digitized and then transferred over fiber optic out through the RF cabin through waveguides into a separate reconstruction computer. I've mentioned this RF cabin several times and the waveguides that go through it. Because we are dealing with very small amplitude RF signals coming from the patient, we need to ensure that the system is isolated from any external radio frequencies which may overwhelm the small signal coming back from the patient. So therefore the scanner or the magnet is enclosed in a 6-sided metal cabin or box, sometimes called a Faraday cage, that isolates the sensitive electronics inside from any external radio frequencies. And it also means that the high energy radio frequencies, pulses, that we generate as part of the imaging process cannot leak out and interfere with potentially adjacent MRI scanners. Then we also have the patient table that moves the patient to the isocenter of the magnet where the uniformity is greatest. This table also supports physiological interfaces. For example, we may want to do a scan synchronized to the patient's ECG, so we can look at their heart, for example, or we may wish to synchronize the acquisition to the patient's respiratory motion so as to minimize artifacts from breathing. We also have a host computer where the MR scanner operator, the radiographer, enters the patient demographics and the required scan parameters. The host computer communicates with a device called the Pulse Programmer that takes all the geometric information like the field of view, slice thickness, and calculates the desired gradient and RF amplitudes for those parameters. And it also handles the synchronization between the gradient pulses and the RF waveforms. The Pulse Programmer sends these waveforms and controls the timings to the amplifiers, which generate the very high voltages and currents required to drive the gradient coils. It also sends the digital RF waveforms to the RF transmitter and amplifier that generates the high intensity RF pulses, again through these filtered connections to the body coil. The signals that are detected by the receiver coil go to this RF receiver and spectrometer, and they get converted to optical signals that are then passed through the RF cabin to the reconstruction computer, which performs a task such as the fast Fourier transformation that is used to reconstruct the images. The reconstructed images are then sent to the host computer for display. We will now look at the role of the individual components that make up the MRI system, starting with the magnet. Its main role is to create this nuclear polarization that we've talked about before, so we know that there is about a 0.001% difference in the number of spins in the low energy state compared to the high energy state, and this difference is what contributes to our net magnetization. We also know that the magnetic field causes nuclear precession, and that allows us to create transverse magnetization that can be detected and used to form the image. In terms of performance specifications, the strength of the magnetic field is very important as to a first order approximation, and if we ignore a lot of other effects, the signal to noise ratio in our images is proportional to the strength of the static magnetic field. Hence the interest in going from 1.5 Tesla to 3 Tesla, and for potentially going to higher fields such as 7 Tesla and above, although there are still lots of technical challenges associated with ultra-high field MR imaging. The uniformity of the magnetic field is also very important in terms of the dephasing of the transverse magnetization, so we need to ensure that the field is as uniform as possible. The field also needs to be quite stable over time, so that whatever method is used to generate the magnetic fields, it needs to have a very good level of temporal stability. We also need to consider the spatial gradient of the static magnetic field. This has nothing to do with the gradients that create the images. This is the variation in magnetic field that falls off with distance from the magnet. And it is this variation in field with distance that is responsible for the projectile effect of ferromagnetic objects that may be inadvertently brought into the MR environment. We also need to consider the fringe field from the magnet. Current MR safety guidelines state that the fringe field must not exceed 0.5 millitesla or 5 Gauss in any adjacent publicly accessible areas, such as corridors or rooms adjacent to the MRI system. The space that contains the 0.5 millitesla field is known as the MR environment. This may mean that additional static magnetic field shielding may be required to be installed in the wall or possibly even the ceilings or floors of the MR environment, depending on adjacent areas, which may contain equipment that is particularly sensitive to magnetic fields, such as photomultiplier tubes in nuclear medicine gamma cameras. There are several field strengths at which commercial MRI systems operate. This is my classification of them. Low field strength systems are generally below about 0.6 Tesla. Midfield is exclusively 1.5 Tesla, whilst high field is now exclusively 3 Tesla. Ultra-high field systems are 7 Tesla and above. There are now many 7 Tesla systems around the world, some of which are even approved to be used clinically. For research applications, there are even higher field strengths available on a custom build basis. For example, there is a 10.5 Tesla whole body system in France, which has gone live fairly recently. There are also various technologies for creating magnetic fields. The low field systems typically use permanent magnets, such as this example here, where the pole pieces are made from neodymium iron boron with a large iron former. This system here has a vertical magnetic field with quite good patient access, which is often marketed to patients who would otherwise feel claustrophobic in the enclosed superconducting systems. There are very few iron cored electromagnets around. The example here is actually a 0.6 Tesla system developed by Raymond Damadian's company Phonar that is called the stand-up MRI. This system is particularly useful for looking at loaded joints or joints where pain may only occur in certain positions that could not be achieved in conventional cylindrical superconducting magnets. In this case, the magnetic field is horizontal. The downside is that the iron former here weighs approximately 111,000 kilograms, and it requires a 100 kVA power supply and an additional 47 kVA power supply just to the water chiller to dissipate the heat generated in the windings. To generate fields above about 0.6 Tesla, here it is really necessary to move to superconducting magnet technology. This is a 3 Tesla superconducting magnet using niobium titanium windings, and providing the windings are below the superconducting transition temperature, then they become superconducting. For niobium titanium, we put them in a bath of liquid helium at 4.2 Kelvin. There are also a lower field strength superconducting system, here using so-called high temperature superconductors like magnesium diboride that has a transition temperature of about 39 Kelvin. In this case, liquid helium is not possible, and it's possible to keep the windings that make up this horizontal field system at the required temperature by using the same kind of cryocooler that we use in superconducting or conventional superconducting systems to keep the windings at around 39 Kelvin. For field strengths above about 10 Tesla, it's necessary to move to different types of superconductor made, for example, from alloys of niobium and tin. If we look in a little bit more detail at a superconducting magnet, this is the only way to generate relatively strong magnetic fields above about 0.05 Tesla. And as already discussed, they range from around 0.5 Tesla to 10.5 Tesla and above for research. Magnets have very good spatial uniformity, less than 1.1 part per million variation over a 40 centimeter diameter spherical volume within the middle of the magnet. They also have a very good temporal stability. And to minimize the extent of the 0.5 millitesla fringe field, they are also actively shielded. If we look inside the magnet here, we can see the magnet windings, which are along here, sitting inside the bath of liquid helium. The number and turns and spacing of those solenoidal windings there are very carefully calculated by the magnet designers in order to produce the most uniform static magnetic field in the center of the magnet. There are several internal radiation shields that are mechanically cooled by the cryocooler, as well as layers of vacuum. And outermost here we have the active shielding coils, also superconducting, sitting in a bath of liquid helium. The current runs in the opposite direction of these coils, and that helps to cancel the fringe field from the main magnet coils. Active shielding also means that the fringe field falls off very rapidly with distance, which means sighting the magnets is much easier, but it does mean there are quite steep spatial field gradients around the magnet, which can potentially increase safety concerns. Older magnet designs typically contain around 2,000 litres of liquid helium, with newer designs coming onto the market now which probably only require around 7 litres. Helium is created as a byproduct of radiation decay, so it is mined in a few places around the world. It's a non-renewable resource and therefore currently quite expensive per litre. But as mentioned, the cryocooler helps to minimise the boil-off, and most magnets these days are claimed to be effectively zero boil-off. As we've already mentioned, when the MRI system is installed, the service engineer arrives with a power supply and slowly injects current into these windings to ramp the field. A 3 Tesla magnet will typically require around 600 amps, providing a stored energy in the region of 15 megajoules. The power supply will then be disconnected, and since the windings have zero resistance, the current will continue to circulate indefinitely, providing the magnet remains superconducting. And that will of course generate our strong static magnetic field. The vast majority of MRI scanners, the permanent magnets and of course the superconducting magnets, are never turned off except in an emergency or from serious maintenance work. A typical 3T magnet probably has approximately 60 kilometers of niobium titanium filaments, which are embedded in a copper matrix. The copper is there because in the event of the magnet ceasing to be superconducting, which is often referred to as a quench, that large energy store will be converted to heat, and the copper will conduct the heat away, hopefully without melting the magnets and irretrievably damaging your magnet. To ensure that the uniformity of the magnetic field is as good as possible when the magnet is installed, the magnet is physically shimmed by the engineer after it has been ramped to the desired field, so that the effects of any steel within the walls or girders above or below the magnet can be taken into consideration. So inside the room temperature bore of the magnet, there will be a large number of these shim trays, where shims, which are effectively just small steel pieces, are put into appropriate locations in the shim trays. A separate system is then used to iteratively plot the field in 3 dimensions and calculate the amount and position of the shims inside these trays. The main role of the gradients is spatial encoding. So the gradient fields need to point in the Z direction but spatially vary in X, Y and Z. Gradients can also be used to encode motion, for example in diffusion weighted imaging, and they can also be used to dephase unwanted signals. Gradients can also be used for dynamic shimming to further improve the uniformity of the static magnetic field on a per patient basis. In terms of performance specifications, we are looking at the peak amplitude achievable in millitesla per meter, the rise time from 0 to the maximum value typically in microseconds, the linearity of the gradients over a defined field of view, and we are also looking to have minimal interaction with other conducting structures such as a magnet cryostat. The gradients typically induce eddy currents in the cryostat, and the magnetic fields generated from those eddy currents then distort the gradient waveforms. So lots of work goes into minimizing that interaction. In terms of the limitations, gradient switching can generate quite high levels of acoustic noise. So there is a requirement to ensure that patients and anybody else who happens to be in the MR environment during the scan has appropriate hearing protections. In order to generate the high performance gradients, we require substantial currents and voltages to be generated in the amplifiers and then passed through the gradient coils. So both the amplifiers and the gradient coils themselves need to have a chilled water supply in order to dissipate the heat that is generated. Finally, gradient switching can cause peripheral nerve stimulation that can range from a tingling sensation to, albeit very rarely, painful muscle contractions. Gradient pulses are generally trapezoidal in shape, and the gradient coils necessary to create them sit inside the room temperature bore of the magnet. The Z gradient is creating using a Maxwell pair, so two counter-rotating currents, whilst the X and Y gradients are created using a quadrupolar design, otherwise known as a Golay configuration, with two north poles and two south poles. The X and the Y gradients are simply rotated 90 degrees with respect to each other. In reality, modern gradient coils are considerably more complex in terms of their design, so our simple Maxwell pair are actually overwound at either end, whilst the Golay configuration has the typical fingerprint type designs. These designs improve the efficiency and linearity of the gradient coils. We also need very high power amplifiers to generate the gradient pulses, and we are typically looking for amplifier power on the order of 1 to 3 megawatts. We need very high voltages to overcome the back EMF in switching on the gradient, so that the rise time is as short as possible, and relatively high currents in order to maintain high amplitude pulses. The gradient amplifiers and coils generate large amounts of heat, so we need to dissipate somewhere between 25 to 75 kilowatts. So the gradient amplifiers and gradient coils are water cooled. In many cases, the gradient conductors are tubular so that the coolant can travel directly through the windings. Vertical or horizontal field systems have planar gradients built into the pole pieces at the top and bottom. So the vertical Z gradient is a Maxwell pair with currents running in opposite directions, and the X and Y gradients are effectively planar quadrupolar Golay designs. Of course, the gradient performance for these systems is generally inferior to what can be achieved on a superconducting system. Looking at the radio frequency side of things, the design of the transmit coil depends very much on the orientation of B0 compared to the subject. Remember that B1 needs to be orthogonal to B0. For example, if we have this vertical field system, then we can generate the rotating B1 field using a solenoidal coil. Whereas in a horizontal field superconducting magnet, where the coil is in the same plane as the patient, we need to generate our rotating B1 field using a so-called birdcage coil. This is the RF excitation arrangement for a birdcage coil inside a superconducting magnet. As we've discussed before, the RF envelope dictates the bandwidth of the associated slice thickness. This envelope is then mixed with the Larmor frequency for the desired slice offset. This pulse is then applied to the input of the RF amplifier, and in order to create a circularly polarized B1 field, the output of the amplifier drives the birdcage coil at 2 points, 90 degrees physically apart, and with a 90-degree phase shift of the waveform performed using this quad hybrid electronic component. This picture shows a typical 16-rung birdcage body coil that is positioned inside the gradient coil assembly. The requirements of the RF transmit side, or B1 plus, is to nutate or tip the net magnetization. We establish a circularly polarized B1 field inside our birdcage coil, shown as the yellow arrow precessing the laboratory frame of reference. Because that frequency is resonant with the precessional frequency of the nuclei at the desired slice location Z, then whilst the slice select gradient is applied, we can tip the net magnetization, the red arrow here, into the transverse plane. The nutation angle is given by the integral of the RF pulse envelope. In terms of performance specifications, the system is characterized by the peak RF amplitude that is available in terms of microtesla, and the uniformity of the transmit field within the coil, which can be expressed as a percentage of the nominal flip angle. The main limitation of the RF system is in the maximum power that can be deposited in the patient, because of the eddy current induced heating in the conducting tissues caused by the B1 field. This power deposition is known as the specific absorption rate, or SAR, and is limited as part of the MRI system specification. We shall discuss SAR in more detail later. The role of the radio frequency receive system, or B1-, is to detect the precessing transverse magnetization that induces the small voltage in the receiver coil. This signal is then amplified, as we can see here, in which case the precessing magnetization is dephasing in the transverse plane in the laboratory frame of reference, and we can see the typical free induction decay signal being shown here. The performance specification of the receiver coils are firstly that they should have a very good filling factor. This means that the coil needs to fit the anatomy of interest as closely as possible to maximize the signal and therefore the signal to noise ratio. Ideally, the received field should be uniform, but the trend these days is to have multi-element array coils that are very good at detecting the signal very close to the elements, but not quite so sensitive to signals deeper in the body. However, there are several other advantages from having dense arrays of smaller sized coils. However, each coil element must be connected to its own separate receiver channel, and then the images from each receiver need to be finally combined. The receive chain should also minimize the amount of noise amplification. This has led to manufacturers digitizing the signals closer to the coil elements, and in some cases actually including the analog to digital converters into the coil design, and then converting the signal to optical for transfer to the reconstruction computer. The basics of any coil, whether that is for transmit or receive, is that the coils are resonantly tuned circuits. So the coil itself will have inductance and resistance, but then we add additional capacitance to ensure that it has a frequency response near the Larmor frequency. The capacitance also ensures that the transmit coil has a matched 50 ohm impedance to allow proper power transfer from the RF amplifier. Coils will generally have a relatively low Q to ensure that they are still resonant for a range of patient loadings. As already mentioned, receiver coils are generally made of several small individual coil elements. Each coil element is sensitive to a small volume of interest, thereby minimizing the amount of noise that is detected. But the use of multiple elements ensures that we have the desired coverage. The original coil arrays, known as the phased array designs, required that the elements be appropriately overlapped, so there was minimal mutual interaction or induction between the coil elements, so that the response from the individual coils just did not appear to come from one large single coil. As the number of elements in coils has increased, then there is now generally some spatial separation between them. This variation in spatial sensitivity profiles allows for more advanced acquisition and reconstruction methods that can be used to accelerate MR image acquisition. There are a wide variety of different receiver coils with different numbers of channels. Here is a list of potential coils that you could purchase from your MRI vendor. Here, for example, is an 8-channel breast coil, an 8-channel brain coil, a 12-channel abdominal coil, and here a 32-channel cardiac coil. As already mentioned, each coil element is connected to its own receiver system, so images are reconstructed from each coil individually. So here on this simple schematic of a 4-coil element, we can see the individual coils, and then these images are combined to produce the final image. So we can note that the individual coil images have a spatial sensitivity that falls off with distance. However, this is somewhat compensated by the reconstruction or the combination of the coil images. This is a typical architecture of a modern MRI receiver channel, and as we have said, we have one of these receiver channels for every element that makes up our coil array. So in this case we have 4 coil elements and therefore 4 receivers. Each receiver takes the analog voltage from the coil following some low noise preamplification, bandpass filtering and some variable gain measurements. The analog signal is then digitized. Now we know that the range of useful frequencies that are encoded in the MR acquisition process is in a relatively small audio frequency range, such as an example here, plus or minus 16 kilohertz. However, in order to make MRI work, these frequencies are centered on the much higher Larmor frequency, for example 128 megahertz at 3 Tesla. Therefore, the signal must be demodulated to eliminate this carrier frequency. We are then left with a plus or minus 16 kilohertz audio frequency signal. This demodulation is typically performed in quadrature, so that we actually end up with a complex raw data where the two components are known as the in-phase and quadrature. Following Fourier transformation in the reconstruction computer, we also get complex data coming out, known as the more conventional real and imaginary components. It's perfectly possible to calculate real, imaginary, and even phase images. However, we generally just deal with the magnitude. As you can see, there are a number of phase errors here which would require correcting. We have already seen the use of the real images in inversion recovery sequence in the last lecture. Those images also required phase correction before they could be displayed. The signal-to-noise ratio in MRI images is dependent on a large number of factors, including relaxation times, the type of pulse sequence used to acquire the data. But this equation shows some of the acquisition features and how they influence the SNR. So firstly, we should note that the SNR is proportional to the size of the imaging voxel, where delta X, delta Y and delta Z are the pixel sizes in X, Y and Z direction, with delta Z typically being the slice thickness. The SNR is also proportional to the square root of the number of samples in the frequency encoding and phase encoding direction, as well as the square root of the number of signal averages. If we just repeatedly acquire the data and just add the data together and then divide by the number of averages, then we can improve the signal-to-noise ratio. The signal-to-noise ratio is also inversely related to the square root of the receiver bandwidth. You should remember that if you're using this equation to look at changes in signal-to-noise ratio, remember that some parameters are interdependent, so that if we change the matrix size for a fixed field of view, we may also change the acquisition time as well as the pixel size. The final component of the MRI system hardware is the reconstruction engine, and its role is to manage the raw data, particularly as higher resolution multi-coil data may generate very large volumes of raw data. The reconstruction software will be optimized to run multi-dimensional fast Fourier transforms as is needed for this multi-coil 3D acquisition of over 200 slices. The recon system will also have to perform the multi-channel image combination as well as any other additional image processing that is required. And in today's world, most of the MRI system vendors are now incorporating deep learning algorithms into their reconstruction pipelines. Some of the performance specifications we should be looking at are the capacity to hold large volumes of raw data, certainly transiently. We do not routinely store or archive raw MRI data, only the reconstructed images. There should be a range of reconstruction algorithms that are available, including not only conventional Cartesian or line-by-line acquisitions that we've looked at previously, but the increasing use of non-Cartesian trajectories, such as this radial acquisition, where the data will require regridding onto a regular grid prior to Fourier transformation. The reconstruction and post-processing speed is governed by whatever hardware processors are incorporated into the system, and as we said, with the increasing use of machine learning and deep learning algorithms, a number of these cutting-edge reconstruction systems are now GPU based. This slide is to give you some indication of the current trends and developments in commercial MRI systems. One vendor is now offering a 1.5 Tesla superconducting magnet that only requires around 7 litres of liquid helium to remain superconducting, which makes siting the system somewhat easier as you do not have to have a quench pipe. There are also research and development activities to develop and build ultra-high field magnets at 10.5 Tesla and above. Conversely, a ultra-low field 64 millitesla portable MRI system has recently come onto the market, allowing the MRI scanner to be taken to the critically ill patients that themselves cannot be moved down to a conventional MRI facility. Again, The low signal to noise ratio associated with that very low field strength is very amenable to image reconstruction algorithms using deep learning. In terms of gradients, vendors are working on providing higher performance gradients with wider bore scanners. Since the power required to drive a gradient coil scales with the fifth power of its radius, these energy requirements can be quite substantial. One way to obtain higher performance imaging, but just for the brain, is through the development of head-only magnets and head-only gradient coils. By virtue of their much smaller radius, they can achieve extremely high gradient performance, albeit only over a limited field of view. RF coils are increasing in the density of channels with 64 or 96 elements, even 128 elements starting to become available. Vendors are also developing very light and highly flexible coils, almost like blankets or potentially wearable coils. Optimization of the static magnetic field, this shimming process we've talked about before, can also be improved by the fact that some groups are looking at integrating higher order shims into the receiver coil elements. So this means that we can really improve field uniformity over quite small fields of view. And then finally, all of the vendors are actively working on developing wireless coils without the bulky cables and connectors that are currently being used. In terms of acquisition, pulse sequences are becoming more sophisticated in terms of image contrast and reducing acquisition times. These methods generally also require more sophisticated reconstruction algorithms using iterative algorithms and, as I've said before, machine learning and deep learning to improve signal to noise ratio and reduce some image artifacts. There has also been a significant amount of work in recent years in academic circles in the development of open source reconstruction tools. MRI is also now combined with other imaging techniques to create hybrid modalities, such as PET-MR, where we can acquire simultaneously MR data and positron emission tomography data, which use solid-state PET detectors that are insensitive to the magnetic field. Combined ultrasound and MR systems have also been developed to leverage the speed of ultrasound with the soft tissue contrast of MRI. MRI is also becoming part of therapy, with several combined MR linear accelerator systems in clinical use, enabling organs to be tracked in near real time and to allow even more precise radiotherapy delivery. Finally, the use of MRI for neurosurgical intraoperative imaging is now well established. An MRI system is installed in the operating theatre, and the surgeons can then rapidly move the patient from the surgical area into the scanner to check that their resection margins are appropriate at the time of surgery. An important part of MR physics is understanding the safety issues associated with MRI. MRI scanners have killed both patients and staff, as well as causing life-changing injuries. Actually, it's unfair to say that MRI scanners have killed people. Obviously, it has been the staff members who have misused the system or allowed unsafe persons or patients with unsafe implants to enter the MR environment who are ultimately responsible for these deaths and injuries. The seminal event for MR safety was the death of 6-year-old Michael Colombini 20 years ago. Michael had had a brain tumour resected and was brought down to the MRI scanner for a post-operative scan under sedation. During the scan, Michael's oxygen saturation started to drop and the anaesthetist called for oxygen. Unfortunately, the piped oxygen in the magnet room was not working, and the MR technologists went off to reset the system. Whilst they were away, a nurse had free access to the MRI facility and heard the anaesthetist calling for oxygen. She saw an oxygen cylinder in an adjacent room and brought it into the magnet room. As the article says, the tank, about the size of a fire extinguisher, became magnetized and flew through the air at 20 to 30 feet per second and fractured the boy's skull. Unfortunately, Michael died from his injuries. 9 years later, the case was settled for $2.9 million. And just to show you how scary these effects are, this is the effect of an oxygen cylinder being located inside or being moved into the bore of a 1.5 Tesla magnet. You certainly wouldn't want to be lying inside the magnet when that happened. In the UK, MRI safety guidance recommends that the MR suite be demarcated by 3 areas. Firstly, the MR environment is a volume, shaded here, that contains the full extent of the 0.5 millitesla magnetic field around the scanner. Note that this volume can extend into other rooms, such as the MR technical room at the back. An MR controlled access area is also defined that contains the MR environment. As the name suggests, the MR controlled access area is restricted and only accessible through the minimum number of self-locking doors, with appropriate warning signs being displayed at all the entrances. And then there is also defined a projectile zone, which is the volume containing the full extent of the 3 millitesla or 30 Gauss magnetic field contour around the scanner. This is the field at which you would start to expect a ferromagnetic object to have some force of attraction or torque. However, only certain equipment that is deemed MR safe or MR conditional, with the specific conditions stated, are allowed inside the MR environment. Any equipment that needs to be taken into the MR environment needs to be labelled as either MR safe or as MR conditional, where the conditions for use can be met in that facility. All other items in the controlled access area which are potentially movable should be clearly labelled as MR unsafe. This patient monitoring system, for example, has an MR conditional label affixed to the base, dictating as to which field strength and which spatial field gradient it can be taken up to. Such labelling also extends to devices that are implanted in the patient, whether they are passive, such as a hip replacement, or active, such as a neurostimulator. The main risk for ferromagnetic projectile incidents is the spatial gradient field, or how the magnetic field falls off with distance from the magnet. The use of actively shielded magnets means that this field can reduce quite rapidly with distance. The ferromagnetic attraction force is proportional to the magnetic susceptibility of the object, the volume of the object, the static field if the object is magnetically unsaturated, and most importantly, the rate of change of the field with distance from the magnet. MRI manufacturers are now required to provide plots of this spatial gradient with position, and here we can see that the highest spatial field gradients happen to be nearest the magnet itself. But if a patient were to be entered into this magnet with an implant of some description, there is no path into the magnet that does not pass through the entry spatial gradient contour, in this case of 250 Gauss per centimetre, or 2.5 Tesla per meter. Manufacturers are also required to provide measurements of the distance from the center of the magnet to the peak field, the position of the peak gradient, and the product of the peak field and the peak gradient. Therefore, it is this spatial gradient that dictates the safety of certain MRI conditional devices or patients with implants with conditionals requirements going into the magnet. I have already mentioned the possibility of a magnetic field quench. This can happen when the magnet suddenly ceases to be superconducting and the stored energy is converted to heat and the liquid helium is vaporized with a 754:1 expansion ratio. When this happens, the pressure inside the magnet rises and the burst disk ruptures and the helium vapor is vented to the outside through the quench pipe. I certainly hope that this quench pipe actually isn't connected to a magnet, otherwise I certainly wouldn't want to be standing there. There have also been situations whereby the helium gas has vented into the magnet room, and at least one situation the pressure overload in the room has prevented the inward opening magnet door from being opened. Therefore, the current advice is that all MRI magnet doors should open outwards. As we've already discussed, the helium gas is extremely cold and therefore there are risks of cold contact burns. Helium displaces oxygen, so there is also a risk of asphyxia, and there is also a potential explosion risk because the temperature is cold enough to liquefy oxygen from the air. Now, just to show you what a quench looks like, here's a magnet that was being de-energized. Here is the quench pipe, and there we can see as if we were electing a new pope. Again, not quite sure I would want to have my van in the path of that or any part of my anatomy. The magnetic field gradients are about 100 times weaker than the static magnetic field and switch in the region from 0 to 5 kilohertz. Gradient scanning can induce peripheral nerve stimulation, which can range from a mild tingling sensation to a painful muscle spasm, a bit like a little light tasering. So patients should therefore not have their hands clasped so as to create large loops in which large currents can be induced. The other safety concern with gradient switching is the acoustic noise that is generated. In fact, the old MRI scanners used to have amplifiers which are typically used at rock concerts. So in certain pulse sequences, the acoustic noise levels can exceed 100 dBA. It's therefore necessary to ensure that anybody inside the MR environment or the magnet room during imaging has suitable hearing protection. The other major risk of serious injury in MRI is associated with the radio frequency field. Although the RF fields are 10,000 times weaker than the static magnetic field, they do switch between 8.5 and 130 megahertz depending on the strength of the static magnetic field. Because tissue is conducting, this alternating magnetic field will induce concomitant electric fields known as eddy currents within the tissue, and then the electrical resistance of the tissue then results in joule or ohmic heating. So essentially we end up with an inductive heating process. And so while tissue heating is strictly controlled, anything electrically conducting about or in the patient can also heat up. Now, the frequencies used in MRI, as I say, mainly cause this ohmic heating with a very small contribution from dielectric heating, as is used in a microwave oven. So less than 1% of the energy dissipated in a patient is used to tip the nuclear magnetization. The vast majority produces nothing but undesirable tissue heating. The specific absorption rate, or SAR, in watts per kilogram is defined as the conductivity sigma multiplied by the induced electric field squared divided by the tissue density. The SAR for a particular pulse sequence is estimated by the MRI system manufacturer, whilst the limits are defined in an international standard, IEC 60601-2-33. The right-hand side of this slide shows the derivation of an estimate of the power deposition in a spherical object with a uniform conductivity. Integrating over the spherical volume results in a fairly standard equation that is used to describe SAR. The important thing with SAR is to note, first of all, that SAR increases with omega naught or B naught squared. That's to say the static field strength squared. So going from 1.5 Tesla to 3 Tesla results in a quadrupling of the power deposition for a given RF pulse. Similarly, SAR increases with the flip angle squared. So going from a 90-degree pulse to a 180-degree pulse also results in a quadrupling of the power deposition. And SAR also increases with patient size. So since SAR is actually measured in terms of watts per kilogram, it's important that the correct patient weight is entered into the scanner when the patient is registered for their scan. So in terms of these exposure limits, IEC 60601 is part of a series of international standards for medical electrical equipment covering their basic safety and essential performance for both equipment and safeties. Part 2-33 discusses the particular requirements for the safety of magnetic resonance equipment for medical diagnosis. And this table shows the exposure limits for RF in typical MRI systems. An MRI scanner can be operated in either the normal or the first level controlled mode, and very rarely in a second level control mode. And in the first level mode, for example, the whole body power deposition cannot exceed 4 watts per kilogram. The manufacturers will also provide some form of SAR monitoring, and in this case here we can see both the 10-second short duration SAR being monitored, as well as the SAR mentioned here, which is averaged over a 6-minute period. So in this case the scanner is in the first level controlled mode, so the whole body SAR peak there is 4 watts per kilogram over any 6-minute period. We also look at the MR magnet room temperature as well, because obviously if that temperature increases, then it becomes so much more difficult for the patients to actually lose the heat that they absorb from the RF pulses. RF burns have been particularly noted where there is a small area of skin-to-skin contact. The burns are generally due to the limbs creating large diameter loops, and where the loop is closed, the point of greatest electrical resistance occurs. Interestingly, unlike touching a hot object, these burns are not happening at the skin surface, but in the fatty tissue immediately below the skin where there are no pain receptors. So patients could be burned, but until that burn damage has an opportunity to propagate through to the skin, there is no sensation of pain and no observable evidence of a burn. Therefore, the manufacturers recommend that thick insulated pads should be used to avoid skin-to-skin points of contact. And in addition, the capacitors within the body coil can also create very strong electric fields, so the patient should also have padding to avoid direct contact between any part of the patient's anatomy and the bore of the MRI system. This is an example of a euphemistically called MR warming event that was not reported by the patient at the time of the scan, but several hours later. So here we can see that there's quite substantial reddening of the skin, and 1 week on we can see that this has now turned into a first-degree burn, and it's probably most likely that this patient was not properly padded as shown in the previous slide. So burns are now starting to be reported from patients who attend for an MRI wearing their fitness clothing that has these invisible silver microfibers woven into the material. Silver is reported to stop the odor-causing bacteria that occurs when you sweat from reproducing. However, it also nicely conducts the MRI-induced eddy currents, resulting in injuries. This slide is from a recent paper that reviews all MRI-related adverse events that have been reported to the US Food and Drug Administration. As you can see, just under 1,000 thermal images were reported, with projectile incidents accounting for 133 events. 86 events were related to acoustic injuries, which included both temporary or permanent hearing loss and/or tinnitus. Of course, this data should be put into the context of the millions of MRI scans that are performed every year throughout the world without any incident. Before undergoing any MRI scan, patients are given a safety questionnaire and consent form where they are asked various questions to determine whether or not they may have any metal on the surface or inside their bodies. Burns have, for example, been reported in patients who have tattoos due to the ferromagnetic content of black inks. Several drug skin patches have metallic backing, which can also cause burns. Any non-ferromagnetic implanted medical object has the potential to heat up, so it's vital that the questions are answered as accurately as possible to ensure that the MRI examination is undertaken safely, or in a few cases that the patient is advised that they should not undergo an MRI examination. So to conclude this lecture, I will briefly talk about the use of contrast agents in MRI. These agents are based on the use of the rare earth element gadolinium. Gadolinium is toxic, so it is chelated to a compound that reacts with the ions to form a stable water-soluble complex. A typical contrast agent that we use is Gadovist, in which the gadolinium is chelated to dihydroxymethylpropyl tetraazocyclododecane triacetic acid, fortunately known as butrol. Gadolinium has 7 unpaired electrons in its outer shell, and since the electron magnetic moment is about 700 times that of the proton, the magnetic moment of gadolinium causes a substantial reduction in the T1 relaxation time of water molecules that interact with the paramagnetic core of the contrast agent. On T1 weighted imaging, a reduction in T1 results in a signal hyperintensity, and the effect of the gadolinium helps to amplify the signal and differentiate pathology from healthy tissue. The gadolinium is administered as a small volume injection, around 10 mils, into a vein in the elbow. To a good approximation, the change in relaxation rate, which is 1 over the relaxation time, is directly proportional to the contrast agent dose at clinical levels, and we have this proportionality constant, which is the relaxivity of the contrast agent itself. So we have equations for both T1 and T2 following administration of the gadolinium contrast agent, but because T1 is substantially larger than T2, the effect on T1 is much bigger, plus the fact that a reduction in the T1 relaxation time wherever the contrast agent affects water molecules in that vicinity will result in a signal hyperintensity, whereas a reduction in T2 on a T2 weighted scan will simply cause a signal hypointensity. So here's a example of a patient with a brain tumor. This is prior to administration of the contrast agent, and this is several minutes after the contrast agent has been injected. So you can clearly see something is going on here, but there's really no clear signal differentiation in this region. However, following administration of the contrast agent, this indicates a tumor with a central necrotic region, the dark side there, and this ring enhancement is most likely a metastasis from a primary cancer elsewhere in the body. There are risks associated with the use of gadolinium-based contrast agents, including allergic and adverse reactions, which are relatively infrequent but can be quite serious, as well as a condition known as nephrogenic systemic fibrosis in patients with renal impairment. Clinical practice is therefore aimed at reducing the incidence of harm by screening subjects for renal impairment before we give them the gadolinium. And also it's recently been discovered that gadolinium accumulates in the kidneys, bones and parts of the brain. Although so far no clinical manifestations or symptoms have been related to this accumulation. However, until further evidence on the potential toxicity associated with the deposition of gadolinium from MRI contrast agents can be established, the MR community is adopting a cautious approach which involves careful evaluation of the benefits and the risks of giving contrast in each individual case. And in particular, one high-profile case, Chuck and Gina Norris tried to sue one of the contrast agent manufacturers for $10 million, claiming that Gina suffered severe side effects from the gadolinium that was administered to her in 2017. However, the Norrises voluntarily dismissed their case at the beginning of last year. So in summary, the main risks associated with MRI are firstly from the static magnetic field, which is ferromagnetic attraction or projectiles, as well as a potential risk from contact with the vapor of helium due to asphyxia and cold contact burns. The risks associated with the time varying magnetic field gradients are primarily transient peripheral nerve stimulation, but also high levels of acoustic noise, whereas the main risk from the radio frequency magnetic fields are induced electric currents that can potentially cause severe burns. After this lecture, you should be able to outline the basic components of an MRI system and their function, and also understand some of the safety issues related to magnetic resonance imaging. So this is the end of my 3 lectures, and hopefully after these 3 you feel comfortable with the desired learning outcomes. If you're interested in further reading about MRI, then there are a huge number of resources on the internet, as well as this book that I co-authored with Richard Ansorge, who is now retired from the Cavendish, but it should be freely downloadable from the university via the link at the bottom. With that, thank you very much.